We continue our lecture on fitting models. So in the last lecture we have, or in the last session, we have fitted the model, so we have performed the regression, and now in this lecture in this session we will see how to assess whether our fitting was good or not. Okay, so the first thing to look at is at the residuals. So the residuals should fulfill a number of assumptions. We will see them more formally in the next slide. But one of the assumptions is that residuals are normal. So if you do a normality probability plot like this one, all the residuals should lie along the identity line or some kind of line. So this in principle would be a good set of residuals, and there are even tests that can tell you whether the residuals are normal or not. You can also plot the histogram of the residuals, and it should look like a Gaussian. Then you can compare the residual to the fitted value. So the fitted value is y. If you make y as a function of x, so the residual should not depend on y, and the residual should not depend on x if you want, so on the observation order. So yeah, this is a little bit more formal. So residuals should follow a Gaussian distribution, and there shouldn't be large outliers, and the residuals should not depend on the predicted variable, and it shouldn't depend either on the predictor variables. So in any one of them, if you're doing a multiple regression, so residuals should not have a dependence with any one of the predictors. And if these conditions are not met, then it might be that there are outliers, or that there are very influential points. We will see later the concept of an influential point in regression, or the model may not be good. So the model cannot explain the kind of observations that you are having. So then in that case you may want to change the model. So this is the concept of the influence of a point. So let's say that we have these points here. We have a fitting that is this blue line, and then we can analyze a couple of outlierness. So for instance, one is called leverage, that is how much x, that is the predictor, is an outlier, and it is a number between 0 and 1. 0 meaning that it is not an outlier. Then you can also analyze the studentized residual, that is how much y is an outlier in terms of the standard deviation of the residuals, and again 0 means that it is not an outlier. This number is not between 0 and 1. And then there is a very interesting number that we can calculate for each point, that is the Cook's d. So the Cook's d tell us how much the regression would change if we remove that point, and 0 means no change. So for instance, we have these points, we have the blue line as regression. If we remove this red point here, how much the regression changes? Then the regression changes from this point, from this blue line to the red line, and that is a small change, and then it corresponds to a small Cook's d. So yeah, we have now very useful tools to analyze why the data is or why the regression is like that. Then we also have R squared. R squared is the fraction of the original variability that is explained by the model. So let's say that we have an observation. So this is y, this is x, this is our observation. we have a number of points that we have not plotted. We have just plotted one of them, just to not clutter the graph. And then we have here the mean of all those points. So this would be the simplest model that we could construct. And then with this simplest model, the total sum of squares, that is the residuals, that are the differences between the different observations and our model. And our model for the moment, it is simply a line. So these residuals, all squared, we have a given error. So let's say that all our points lie in a flat line, horizontal flat line. So then the mean would be a perfect model, and this total sum of squares would be 0. But as long as our points deviate from this flat model, then we will have a non-zero total sum of squares. Okay, so now we have our fitting. So this line, blue line, is our fitting. And then there is a difference again between our observations and our prediction. The prediction is the hat y. And there is a difference between our prediction with our model and the simplest model, that is the mean. So we can summarize all those differences into different parts. So we had before the total sum of squares, but this total sum of squares now we can split it in two parts. One that is explained by the model, and we will call that the explained sum of squares. It is the difference for every point between the prediction of that point and the simplest model, that is the mean. And then the second part is the residual. So the residual is the difference between our prediction and the true observation. And those are variations that we cannot explain. So now we can construct the r squared as the ratio. It is 1 minus the residual sum of squares divided by the total sum of squares. And this r squared then can be understood as the fraction of the total sum of squares that is explained by the model. So if the model is perfectly explaining the data, there is no residual, so the residual will be 0 and the r squared will be 1. Okay, so the meaning of this r squared is the proportion of variation that is due to the explanatory variable. So here in this example, let's say this is mortality versus latitude, and then this is our line that fits the data, and the r squared is 68% or 0.68. So that means that 68% of the variation of the data is due to the latitude. And this r squared and all the tools that we have seen so far, like the analysis of the residuals, the leverage, the Cook's D, and so on, they can all be applied to nonlinear regression too. So if we have a nonlinear regression like this one, where we are regressing the speed at which a chemical reaction is taking place, that is v. So y would be v, and then x would be the concentration of a substrate or whatever. And we have these shapes, these funny shapes given by this function, but still the regression tools that we have seen, the analysis of residuals, the assumptions on the residuals, the r squared, and everything remains the same. Then simply choosing the model that has the minimum r squared is not enough. If we compare several models, the more parameters we have, the r squared will be smaller and smaller for sure. So instead of the r squared, what we can construct is some penalization or some kind of adjusted r squared that penalizes for having many parameters. And researchers have found useful to have this penalization here. So P is the number of parameters. And then if you analyze carefully this formula, the more parameters you have, uh, assuming that the residuals, there is just a small change in the residuals, then the R adjusted, R squared adjusted is smaller than R squared. So we should choose the one with maximum R squared, but without having too many parameters. We may transform this expression into this one, where the R squared adjusted directly depends on R squared. And again, this P is simply a penalization for the number of parameters, and N is the number of observations. So if you have just 3 points, you can always fit a polynomial of degree 2 that has 3 free parameters, and you would have zero error. But that doesn't mean that that polynomial is really a good model. So you should be penalized for having too many parameters. And there are many other penalization schemes. They are a bit more complicated, like the Akaikis information criterion, the sparse Bayesian information criterion, minimum description length, and so on. So if you have multiple models, how do you choose which one is better than the other? So we have already seen one criterion, but this criterion is not automated. So let's see if we can construct a test that is a way to automate the decision of whether to choose the new model or not. So many of these tools, like all these ones here, they are designed for nested models. So nested models are models in which one of the model is a particularization of the previous one, so or the other one. Okay, so let's say that we have polynomials of degree 0, 1, 2, 3, and so on. So the polynomial of degree 0 is a particularization of the polynomial of degree 1 when b is equal 0. And the same, the polynomial of degree 1 is a particularization of the polynomial of degree 2 when c is equal 0. So all models in which one of the models is a particularization of the other, they are called nested models. And for nested models, we can compute, we can have different tests. We will see the partial F test a little bit in more detail. So we have the sum of squares of the residuals by the full model and by the reduced model. We have the number of parameters in the full model, the reduced model, and we have the number of observations. And with all these numbers, we compute the number, single statistic that is called F, and then this F is distributed as a Snedeker F with some particular number of degrees of freedom. We will not enter into that. But the thing is that now you can construct a test and see whether this F is larger than something. If it is larger than something, you reject the hypothesis that the two models, the reduced one and the full one, have the same explanatory power. And there are many other tests for nested models. For non-nested models, you can use the Akaike information criterion or the relative likelihood test. And you can never compare models that have been fitted to different data sets. So all these tests, they assume that the model is fitted to the same data set. Okay, so common mistakes when choosing for models. So we have already mentioned one. So you cannot compare models that have been fitted to different datasets. You cannot use techniques that have been designed for nested models for non-nested models. You cannot compare models whose predictions are undistinguishable in the range of X that you are analyzing. And you cannot fit models that do not make scientific sense. And here we have a simple an example of that. So let's say that the chemical reaction speed as a function of the concentration of the substrate is given by this kind of function. And this function you have come to it after a physical derivation. So there are equations in physics that at the end tells you that this is the relationship between these two. So you cannot fit a logarithm of v as a function of the logarithm of s simply because it fits better the data. So if there are some physical reasons to have this family of functions, then you have to fit this family of functions and not any other family of functions simply because they fit better the data. Then you shouldn't also fit a lot of models and accept the ones that fits the best. And this is kind of multiple testing. So, and we have already seen all the problems that multiple testing brings in. So there are also some other tools to validate our model, how to decide whether our model is good or not. And here we have a few of them. So we have k-fold cross-validation, leave one out, bootstrap. The idea is that we have some points, data points, we feed a regression line or regression curve, and then how do we know that that is a good model? So we could, for instance, leave 1/10 of the data out, so 10% of the data we leave it out, we do the regression with the remaining 90%, and then we see whether this regression explains well the 10% data that was not used for the construction of the regression. And we repeat this process 10 times, so every time we leave a different 10% of the data out. We can take this to the extreme, so if we have n data points, we construct the regression with the n minus 1 point, and then see if this regression line can explain well the data point that was left out. And we can use bootstrap. So bootstrap is a kind of similar thing to the other ones. So we take a bootstrap sample. So if we have n data points, we will have n data points as a random sample, but each point can be selected several times. So this is sampling with replacement. So that means that we take n data points from the original n data points, but because of the replacement, a single point can be chosen several times. And then for every bootstrap sample, we do a regression, and then we can construct confidence intervals on each one of the regression parameters. We can analyze the residuals, we can do many things with those random samples. So this is all for the tools to assess the quality of our regression, and see you next time.